Hi, so we want to look at radioactivity today. By the way, if you want a PDF containing the key points, just DM I want PDF so that I will know and then I can reach out to you. So today we are going to be looking at the introduction to the radioactivity, alpha decay, beta decay, gamma decay, and would also look at half-life. These are the basic concepts of radioactivity. There are also more to this, but at least you should know the introduction, what radioactivity is about. You should know what alpha decay is, beta as well as gamma. So we're starting off with the intro here. So what is radioactivity? Well, that's the question that should pop up in your mind. Basically, radioactivity is a spontaneous disintegration of the nucleus of an atom to produce another atom. So that's the summary. It's a spontaneous disintegration of the nucleus. Of an atom to produce daughter nucleus or nuclei. And this very definition is incomplete. Okay? It's incomplete. I'm going to add something else to it in a minute. But we're definitely talking about having a parent nucleus initially, and then it changes into a daughter nucleus. So that means the genetic composition basically changes. So one atom could change to another with the release of energy, and that's the important thing. So we're going to add that in the definition now. With the release of energy. This energy could also be in form of radiation. So you want to add energy or radiation. Okay, so this is the intro. And after this, we'll be looking at the next thing, which will be alpha decay. So, alpha decay, here we go. So what is alpha decay, or what does alpha decay mean? Alpha decay, also called the alpha particle, is basically produced when you have a certain disintegration that gives out a helium particle. So basically the alpha particle is also known as the helium particle. Bear in mind that helium has an atomic number of 2 and a mass number of 4. So this equation I'm writing here, that's thorium, TH. TH has an atomic number of 90, mass number of 232. It can decompose, that's the parent nucleus there, thorium, to give you a new one here, which is called radium. Radium has a mass, atomic mass of 228 and an atomic number of 88. Now to balance this equation up, you'll see a helium particle being released at the right hand side. Okay, so that helium particle is known as the alpha particle, or you can call it the alpha rays. The alpha rays are actually positive. They're positive rays. You also have beta, gamma. Yes, beta is negative, and we are coming to that as well. So we want to check out what beta decay is now. We've mentioned that it's negative, right? Actually, beta decay is a stream of electrons, and electrons are negative, so we have that E there. and then we're having -1. So -1 is what you have below there, and at the top you have 0. This here is an example of a beta decay. We have lead. Lead is number 82 on the periodic table, and it has a mass number of 212. That could undergo beta decay to give you bismuth, which is 83, with a mass number of 212 as well, and a release of beta radiation. So you see, we have the alpha radiation here, which is the helium particle, positively charged, and we have the beta particle. Okay, so what you have to note here is the fact that the denominators, did I say denominators? I mean the lower subscript there should be equal, because that's an equation, right? So if I have 82 there, 82 should be equal to 83 minus 1 there. Same thing applies here. The 90 should be equal to 80 plus 2, and at the top 232 should be equal to 228 plus 4. Okay, that's one thing you want to take note of. It will ensure that you're writing the correct equation. So it means that one could actually be missing, right? And you will be able to find the missing part because you will basically add them up. So let's look at gamma decay. Gamma decay is different from alpha and different from beta, because for gamma, it's just radiation. Okay, we don't really have to consider those masses too much because it's just purely radiation. So we could have Tc there, technetium, number 43. That's just before ruthenium, and it could change into technetium, still 43 again, nothing changed. It's just that the new technetium now is the new one that follows the gamma radiation. So that's just the difference between the two technetium there. So the gamma rays was released, and see this gamma ray, it's very strong, very strong. So back here the same thing happens. Your top numbers should be equal, and your bottom number should also be equal. We've said this before that the beta is a stream of electrons, yes, which is negatively charged, and then the helium particle, which is the alpha particle, is positively charged. So it means if you should put like an electric field and you pass this radiation, you would have them deflecting accordingly. A gamma rays is just neutral, basically. We've mentioned that it's a strong radiation there, used in curing cancer because it's like super strong. Yes, so what I'm drawing right here now shows the deflection. We have the positive one, the neutral one, and the negative one. What's the positive one? Yep, the alpha particle. So what's the neutral? That's the gamma rays. And then what's the negative one there? That is the beta. So this is the deflection here. In the presence of electric field, it could deflect. The positive one, which is the alpha rays, will deflect to the negative end of the electric field. Okay, this is some physics in here, because radioactivity is actually a physics, chemistry inclined topic. So now I'm going to write an example for you. You see if you can figure out what X will be. Okay, so this example here, I have cobalt, number 27, and it changes to nickel, number 28. That's the parent nucleus cobalt, and then the daughter nucleus is nickel. So what is X? So to do this, you have to ensure that the top numbers are equal, That is the sum of the numbers on the top numbers on the left should be equal to the sum of the top numbers on the right. Okay? And also the sum of the bottom numbers, as the 27 on the left, the only 27 I have there, should be equal to the sum of the bottom numbers, that's 28 plus something. So basically 28 plus something, which is minus 1, should give you 27. So now you can figure out that x is actually having 0 and minus 1. Therefore, you know it's a beta particle. So don't forget this, okay? That technique could actually help you big time. Okay, let's see another one. So I'm going to write radon here. Radon is Rn, number 86. Radon is different from radium, okay? Radon is 26, that's in group 8, or group 18 as you would call it. And it's different from radium. Radium is, in group 2, right? Isn't it? Okay, so we have Rn, which is radon. It changes into X. Same thing there. So basically, if you go back, you'll see that it's just no change. Therefore, you suspect gamma. Alright, so now what we are drawing here is how strong these particles are. Very important part of this topic. The alpha rays are stopped by a thin sheet of paper. That's the alpha rays traveling there, stopped by a thin sheet. The beta rays penetrates more, but again is stopped by an aluminum foil. And the gamma rays, which is a strong one, we've said it before, right? It's a strong one. So it passes through the thin sheet of paper, passes through the aluminum foil, but then gets stopped by something that's thick, like a lead block. So you can say that the alpha rays is basically the lowest penetrating. So it has the lowest penetrating power, basically. Lowest penetrating power. Which one has the highest penetrating power? Exactly, the gamma rays. So if you're told to arrange it or rank it, then you know what to do. So the beta is just in the middle there. Okay, then another thing is really important apart from the penetrating power. We also have what we call the ionizing ability, right? Alpha rays, they have the lowest penetrating power, but they have the highest ionizing ability. Okay, so remember these two side by side. As you're remembering that it has the lowest penetrating power, also remember that it has the highest ionizing ability. So that just implies that, our beta is still medium here in the middle, but then our gamma, which has the highest penetrating power, would have the lowest ionizing ability. So basically, ionizing ability is inversely related to penetrating power. So you have to remember this, okay? Let me write it here. Remember this. Remember this. Okay. So that's that about that. The next thing we're looking at is half-life of a radioactive substance. See this half-life? It's about disintegration, right? So disintegration is important. A definition of the half-life for you is the time that it takes for the amount of a substance to reduce to 1/2 of its original value. Okay, the time it takes for the amount of a substance. It could be amount, it could be concentration, it could be mass, it could be number of moles, it could be number of particles, but I'll just say amount, okay? So the amount of a substance to reduce to 1/2 of its original value. So if we had a concentration of 4 mole per dm cube, the time it will take for it to become only 2 left. That's what we call the half-life. Does this make sense? Okay, now this is the formula for the half-life, 0.693/K, and that's because Usually, this radioactive decomposition follows a first-order kinetics, and that is why this formula, which is the half-life of a first-order reaction, is being used here. Okay? So remember, the half-life of a radioactive substance is given by this formula, 0.693 over K. So what's K? K is a decay constant, and then T half, that's the half-life. For the units, if the T half is in seconds, then the K will be in per seconds. If the T half is in minutes, K will be in per minute. If the T half is in hour, K will be in per hour. If the T half, that's half-life, is in days, then K is going to be in per day. Okay? So this is really important. Like we said, it follows first order kinetics. So we're going to look at questions on half-life next. So we'll see how we can apply this formula. But this is your main equation right here. So you have to remember this one. That helps you get the half-life when given the decay constant. Okay, so look at this. The decay constant for a decomposition reaction is given. How long will it take half of the substance to decompose? So what are they asking here? They're asking, what is the half-life? What is the half-life? So the half-life will just be, unknown for now until we use our equation, that. And then what's our K? Right there. That is our K. So we'll plug that in. 6.50 times 10 raised to the power minus 4 per seconds. So by the time you calculate this, your answer should be in seconds. So you do that calculation and you have 1 times 10 raised to the power minus 3. You see, I want you to do this on your own, right? And see if you get that answer. Okay? Let me know in the comments if you got that answer on your calculator. And a new question here. The half-life of titanium is 20 days. If the initial mass of the radioisotope is 200 grams, that's the initial mass, what mass will remain after 4 weeks? 4 weeks, what's that in days? Because 7 days is actually 1 week, so 4 weeks should be 28, right? 28 days. This is a conversion. If you're having any challenges with conversion, also let us know in the comments. So maybe we might reach out to you personally to have a chat around it. It'll help you improve. Okay, so we can use our half-life formula, right, to get the decay constant because they've given us the half-life. So we can use this formula quickly to get the decay constant. That will be 0.693 over 20. So I decided to work in days, right? And that's why the 28 days was written there at first. Now I'm doing a calculation here to get this value, 0.0347 per day. That's my K. I'll tell you where we're going to use that later on. So now I've gotten my K. I know the initial mass, right? That's 200, but I'm coming to that. Now there's a special formula that we also use here, which is, I'm writing it here, AT equals A naught exponential minus KT. What's AT? AT is the amount left after a particular period of time. Okay, that's the amount left after that decay has been done over a period of time. And the time we're talking about is T, right? That's small t. Here in this question, that time is 28 days. Okay, and that time is this T I've circled up here. That has the same time we're talking about. So right there, we'll be plugging in 28 as well. The K, okay, you already know what K is, right? The K constant. That's what we've solved already. So we're going to plug that one in there. Your exponential, that's about 2.7. You can also get exponential on your calculator. And the A naught there is the initial amount. of the substance. So if the initial mass of the radioisotope is 200 grams, then 200 grams is our A naught. Does this make sense? Okay, so this means that I can say that AT, which is the amount left after, 28 days, right, will be equal to A naught. A naught is supposed to be the initial mass, which is 200, exponential minus KT. What's our K? Right there, 0.0347. I might even choose to put that in bracket. So 0.340347, yes, times the time. What's the time? 4 weeks, which is 28 days. Because we're working in days, since our K is in per day, so we want to also have our time there in days. Okay, now let's solve all this. This will be 200 and exponential minus, if you do that multiplication up there, you should get 0.9716. Also confirm if this particular value is correct from your end, and let's see what you obtain. Now you'll also solve all this out on your calculator and you get 75.70, which is lower than 200. So it makes sense because it's decreasing. It's a decomposition, right? So it's decreasing. So your final answer for AT should be smaller than A naught. Here's my question for you. How do you type this into your calculator? The exponential minus that. How do you type it in your calculator? Let me know in the comments how you typed it, what button you pressed, and you'll also be helping other people when you do that. Okay, so let's just do a summary of everything. From the top, we have seen this. Parent nucleus goes into a daughter nuclei plus energy. Interesting. And our alpha decay. Remember we said alpha decay is a positive particle, right? That's the helium particle, which is positive. Yeah. And then we looked at the beta, which is negative. Remember I said if you need a PDF of this, just write it in the comment section or reach out to me via DM. So I'll send that over. Then the gamma rays is neutral. We said it's very strong, right? It's used in curing cancer. This one here. Super strong stuff. By the way, there's also something called the electromagnetic spectrum, which the gamma ray tops the list. Very strong in energy and frequency too. Really interesting stuff. We'll cover it another day. And then this equation, which you'll be asked to find one missing stuff, and now you can do that. The power of this alpha rays, lowest penetrating power, yes, but highest ionizing ability. So remember this. And then your gamma is the best penetrating but the lowest ionizing ability. What else did we talk about? We talked about half-life formula. C half is just 0.693 over K. We took examples and we took more examples. So this is very, very interesting, and I would like you guys to let me know what you think about this, and also if you need any particular topic in chemistry you want help with, let me know.